Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the annals of mathematical history, 1736 marks the publication of Colin Maclaurin's monumental work, A Treatise of Fluxions. This two-volume treatise represents a profound attempt to provide a rigorous foundation for Isaac Newton's calculus, commonly known as the method of fluxions. Maclaurin's endeavour arose from a particularly urgent need for the rising tide of philosophical skepticism towards the very foundations of calculus, most notably articulated by Bishop George Berkeley in his influential critique, The Analysis. Berkeley's assault targeted the logical inconsistencies and lack of rigorous justification inherent in the use of infinitesimals, those elusive quantities considered to be both non-zero and yet smaller than any assignable magnitude. He famously derided fluxions as ghosts of departed quantities, questioning the validity of mathematical arguments built upon such shaky ground. This critique struck at the heart of Newtonian calculus, casting doubt on its reliability and threatening to undermine its widespread application in physics and astronomy. Maclaurin's treatise stands as a direct and comprehensive response to Berkeley's challenge. He understood that the future of Newtonian calculus hinged on providing a solid, geometrically sound foundation, one that would silence the skeptics and secure its place as a cornerstone of scientific inquiry. To achieve this, Maclaurin turned to the venerable tradition of classical Greek geometry, specifically the method of prime and ultimate ratios expounded by Euclid and refined by Archimedes. This method, rooted in the concept of limits, allowed Maclaurin to sidestep the problematic notion of infinitesimals altogether. Rather than relying on infinitely small quantities, he focused on the ratios of vanishing quantities, demonstrating that these ratios could be rigorously determined through geometric arguments. His approach involved considering sequences of geometric figures and approached a limiting case, the properties of this limit, rigorously established through geometric proof, then became the basis for defining tangents, area, and other fundamental concepts of calc. For example, consider the problem of finding the tangent to a curve at a given point. Maclaurin would construct a series of secant lines approaching the tangent line. Utilizing geometric theorems and constructions, he rigorously showed that as the secant lines converged, their slopes approached a specific value. This value, determined solely through geometric reasoning, then defined the slope of the tangent line, effectively bypassing any need for infinitesimals. Similarly, while addressing the calculation of areas under curves, Maclaurin divided the area into an infinite number of rectangles. He then calculated the sum of the areas of these rectangles as the width of the rectangles approached zero. This sum approached the exact area under the curve. This approach is analogous to the modern definition of the definite integral, but Maclaurin accomplished it entirely through geometric arguments, thereby grounding the calculus in a more secure, intuitive framework. A specific example he provides in Book 1 involves determining the area under a parabola, meticulously demonstrating the geometric progression of inscribed rectangles and their ultimate convergence to the definitive area. The immediate reception of A Treatise of Fluxions within the British mathematical community was overwhelmingly positive. It was hailed as a masterful defence of Newtonian calculus, providing the much-needed rigor and philosophical justification that had been lacking. Mathematicians praised Maclaurin's ingenuity in adapting classical geometric methods to the challenges of the new calculus, acknowledging his success in addressing Berkeley's concerns. It is essential to recognize the direct intellectual lineage that informed Maclaurin's work. Newton's Principia Mathematica, with its geometric treatment of mechanics, served as a primary source of inspiration. Furthermore, Euclid's Elements, with its axiomatic structure and rigorous proofs, provided the bedrock upon which Maclaurin built his geometric edifice. These works furnished both a methodology and a standard of rigor that shaped the very character of Maclaurin's treatise. Maclaurin explicitly aims to prove Taylor's theorem through geometric methods. This achievement seeks to demonstrate the power and generality of his approach. The proof, detailed in the treatise, showcases Maclaurin's ability to derive fundamental results of calculus from geometric first principles, reinforcing his commitment to a rigorous, intuitive foundation. This particular achievement, along with its implications, forms the core emphasis of subsequent analysis. His Treatise of Fluxions, a rigorous exposition, a original geometric exploration of calculus. Maclaurin's A Treatise of Fluxions stands as a monumental response to the foundational challenges levied against calculus, primarily those articulated by Bishop George Berkeley in The Analyst. Berkeley's critique centered on the concept of infinitesimals, which he derisively termed ghosts of departed quantities, questioning their logical validity and the rigor of the fluxional calculus developed by Isaac Newton. Maclaurin sought to answer these criticisms by establishing calculus on a firm geometric basis, following in the tradition of the ancient Greek geometers and Newton himself, who initially presented many of his calculus ideas within a geometric framework. The treatise meticulously constructs calculus upon the principles of Euclidean geometry. Maclaurin believed that by grounding calculus in geometry, he could avoid the ambiguities and logical pitfalls associated with infinitesimals. He achieves this through a series of geometric demonstrations, constructing curves as the limits of polygons and areas as the limits of sums of rectangles. The core concept involves approximating curvilinear figures with rectilinear ones, then rigorously demonstrating that as the number of sides increases indefinitely, the rectilinear figures approach the curvilinear ones. A listener familiar with measure theory may recognize this as an early attempt at defining integration through a limiting process resembling Riemann integration. Maclaurin's geometric approach manifests through his treatment of tangents, areas, and curvatures. He does not introduce infinitesimals as independent entities. Instead, he defines the tangent to a curve through a limiting process involving secant lines. The area under a curve gains definition as the limit of a sum of rectangles, with Maclaurin painstakingly demonstrating that this limit exists and corresponds to the integral. Curvature receives a geometric interpretation, relating it to the radius of the circle that osculates the curve, or best approximates it. At a given point, a key element of Maclaurin's treatise involved providing a geometric proof for Taylor's theorem. It is a notable achievement given the theorem's central role in calculus and its wide applicability in approximating functions. Maclaurin frames the theorem through geometric constructs, representing the function and its derivatives as geometric quantities. His proof involves demonstrating that the geometric representation of the Taylor series converges to the actual curve under certain conditions. This geometric proof, while intricate, showcased the power of Maclaurin's approach and helped solidify the foundations of fluxional calculus within the British mathematical community. Despite its ambition and rigor, Maclaurin's geometric approach possessed inherent limitations. The emerging analytic methods on the continent, particularly those developed by Leonhard Euler, offered a more flexible and powerful framework for calculus. Euler's approach, utilizing algebraic manipulations and power series expansions, allowed for easier generalization and application to a wider range of problems. It also facilitated the development of new areas of mathematics, such as complex analysis, which would have been exceedingly difficult to develop within Maclaurin's geometric frame. Maclaurin's work exerted a significant influence on subsequent British mathematicians. It reinforced their adherence to geometric methods and maintained the Newtonian tradition in Britain, even as analytic methods gained dominance on the continent. Figures like John Landon and Robert Woodhouse, while acknowledging the power of analytic methods, continued to emphasize the geometric foundations of calculus, reflecting Maclaurin's emphasis on rigor and intuitive understanding. The treatise's legacy extends to mathematics education in Britain. His textbook served as a standard text for university students, shaping their understanding of calculus. The emphasis on geometric intuition and rigorous proof influenced generations of mathematicians, fostering a distinctive British approach to the subject. Maclaurin's Treatise of Fluxions represents a pivotal moment in the history of calculus. It showcases an attempt to address philosophical skepticism through geometric rigor, providing a systematic and comprehensive treatment of calculus. While the analytic methods ultimately prevailed, Maclaurin's treatise remains a testament to the power of geometric reasoning and its role in the evolution of mathematical thought. It also highlights the challenges of foundational debates in mathematics and the enduring quest for rigor and clarity. Today, the treatise stands as a historical artifact, illuminating the complexities of mathematical development and the diverse approaches employed in the pursuit of mathematical truth. His work serves as a reminder of the historical contingency of mathematical knowledge, which often evolves through a dialectical process involving both internal logical development and external philosophical challenges.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.